Hey everyone. So my goal for this video is to tell you about this work I did about 5 years ago, it would be now, with Aaron Hertzman on modeling human travel. And the reason I'm talking about this is not because this is the most important advance of science to ever happen. It's because it might serve as a good template for the kind of thing that you might try to do in SML310. Obviously, you don't have to write a paper that's publishable right away, but hopefully you'll get there at some point. So here's the problem that we are addressing. You want to basically model, another word for compute, the probability of going to point B on the globe if I'm starting from point A, right? So let's say that I'm in Princeton, and what I want to do is I want to say, okay, within a day, there is this probability that I'll be in New York. There is this probability that I'll be in Philadelphia. There is this probability that I'll be in Long Branch. And there is this probability that I'll be in Boston. And there's like a probability for basically every location on the globe. And the first thing that you would do if you have a data set of people moving around the globe, as there are several of those in fact, you might say, okay, like what's been done already? So the thing that's been done, so this would be 15 years ago now, and of course, you know, the Levy flight model was known about before, is this kind of thing. So what this says is that you have a probability that's a function of the distance that the person would travel, right? So if you want to know kind of how likely it is that they'll go from Princeton to New York, you'll measure the distance between Princeton and New York, that'll be the D, and you'll compute this formula. So here you have D to the power of minus B tau, right? So tau is the time interval that you take. So if a tau is different, then b tau is also going to be different. In our example, tau is equal to 1 day, right? So you'll compute basically 1 over d to the b tau, where tau is equal to 1 day, and that'll give you an idea of how likely you are to go from Princeton to New York if the distance from Princeton to New York is d. Okay, so one obvious thing is that under this model, we don't care about the direction. So you're just as likely to go northeast as you are to go southwest, right? So you have the same probability of ending up approximately in New York or in Philadelphia, for example. And this is based kind of the application of this kind of thinking is based on this paper by Brockman that came out in Nature in 2006. So of course, Nature, like science, to some extent like the proceedings of the National Academy of Science, PNAS, those are really fancy venues with papers that are considered in some ways important, if not necessarily kind of like the premier journal. Those are not like, for example, the premier journals for results in economics or something. But if people get a neat kind of interdisciplinary result, they would publish it in Nature or Science or something like that. So that's one approach. So the other approach that exists in literature, and that's from a paper by Kalogerakis and co-authors. In fact, one of the co-authors is Aaron Hertzman, my current co-author. So here we're doing something a little bit different. Here what we're saying is we'll index all the locations on the globe using those i's and j's. So essentially I denotes a location like New York, Philadelphia, whatever, as does j. And this pij tau, what it is the probability of going from location I to location j within time interval tau. So how would we compute it? Well, the intuition, and it's expressed in this formula, the intuition is, well, we'll see how many people started at I and after time interval tau ended up at j. and that's going to be nij tau. And that will just divide it by the total number of people who started at I and ended up somewhere after time interval tau. So we are adding up all those nil tau. So nil tau, the number of people who started at I and went to L, and it took them time tau. And we're just like adding all those people. So basically all the outgoing traffic from location I, and what we divide by this is the total number of people who went from location I to J in time tau, and that gives us, and that should be kind of intuitive, that the larger this number is, the larger the probability of going from location I to location J in time tau. Okay, so basically if you have a data set of people moving around, you can just compute those Pij taus. There's complications, but this is basically it. Also, if you have a data set, you can figure out, okay, so what are the B taus that best fit my data set of, for example, people moving around. So thinking a bit more about the Levy flight model, right? So technically, this would be the marginal probability distribution of traveling distance d given time interval tau. And so this is called, well, this is not expressed as a power law, but rather it's expressed as a power law, but not as a truncated power law. But that's just basically a name for this formula. So the thing to say about it is it's a long tail distribution. Long tail distribution means that you can have a wide range of distances between source and destination, for which the probability would not be super small. Okay, a distribution without long tails would just have a small range of these that are possible. And it's used, like I mentioned, for modeling human travel, but also modeling kind of sharks swimming around in the ocean. And there's a picture of a shark if you like. And the thing to say about it, like we said already, it's not directionally variant, so we are just caring about what's the probability of going like 100 miles, right? It's also not spatially variant, right? So, like whether I'm going from Montreal or whether I'm going from Kansas City, the formula is going to be the same, because all the formula cares about is the distance from my source to whatever my destination is. And that doesn't actually make sense. So both Montreal and Kansas City actually have airports, but if you're starting from a really remote destination that doesn't have an airport, for example, it would stand to reason that you travel less, certainly in the amount of time it would take you to go to the airport. So if you're 6 hours of drive from the airport, there's no way that you'll go, more than 600 miles. Whereas if you're near the airport, you might go much further. So that was kind of the motivation for us to come up with a fancier model that would be spatially variant, and that would also be directionally variant. Now, I don't necessarily expect people to come up with those kinds of models, but it would be useful having seen the model that I'm about to describe, to see what we did with this model. So okay, so just kind of to set things up, what we do is we discretize the map into J quads. So just think about them as like rectangles on a map, basically, right? The usual thing. And this is kind of like, as opposed to taking the precise GPS coordinates of each location, right? Because if you take the precise GPS coordinates of each location, there's kind of a problem, because that means that if you're going from Nassau Street That's not the same as going from Prospect Avenue because different locations, but we want to say that those locations actually have a lot more in common, so we'll just put them all in the same quad if they're near each other. And that process, we refer to it as discretization because GPS coordinates are continuous, whereas our quads on the map are discrete. We also discretize time into t intervals, and that means that we don't treat time as continuous. We just say kind of time intervals of up to 1 hour, time intervals of 1 hour to 2 hours, time intervals of 2 hours to 4 hours, and so on. And that, again, just allows us to process data more easily. So what's our dataset? Well, our dataset consists of what we call user trajectories, and that dataset, strictly speaking, that dataset is not anymore available, but there are other datasets that are like that are available if you're interested. So the trajectory looks like this. It's like we start out at location 1 at time tau 1, and then we go to location 2, location L2 rather, and the time now is tau 2, and so on, right? So, like we mentioned before, if you want to count up the number of transitions, so with or without intermediate steps, the number of transitions from location I to location J within time tau, that would be Nij tau. And just to mention the data sets that I was working with, we have our, it's kind of a semi-private Flickr data set, and basically what it is like you take a photo, and every time you take a photo, it's geotagged and time-stamped, which means that if you look at the user's photo stream on something like Flickr, you can actually figure out how the person moved around the globe, right? And we discretize the world map into about 3,000 quads, and they're all approximately 400 square kilometers each. So we also used a dataset of Shanghai taxis, which have GPSs installed on them, and there's like a snapshot of the location and actually several other things as well at regular time intervals for the taxis, so you can figure out how the taxis moved around. And we use that as well in order to predict how Flickr users move around the globe, basically, and also try to predict how taxis in Shanghai moved around. So, okay, here is the model that Kalagrakis and co-authors used, right? So this is spatially and directionally variant, right? Because we're taking two specific locations, I and J, and we're computing the probability of going from I to J. And the next thing we can do is we can say, well, like, what if our data set is so small that Nij tau is actually 0 just because you didn't observe anyone going from I to J in time interval tau, but it's not that it couldn't happen, it just didn't happen to happen in our particular data set. But if this is 0, then the estimated probability of going from location I to location J would be kind of literally 0. So that's not good. So there is ways which I'm not going to go into of basically smoothing the data in a way that would avoid obtaining those 0 probabilities. So here you can start to try to visualize the model, and usually what we do is we say so kind of orange is high and green is low, so that's actually, arguably, we should have labeled this. So here what you have is you're starting in New York, and you see that those are the high probability destinations starting from New York, and the green is the low probability destinations. You'll notice that a lot of this is gray. Actually, a lot of the quads in our data set, nobody actually ever goes there in our data set of Flickr users. So that explains all the gray. So this kind of thing is obviously kind of, most of you or all of you are not going to be working with geographic data, right? But saying, okay, I'll try to basically visualize what it is that my probability model is doing. This is one way to proceed in order to make a really good project, right? Because if you come up with a novel way to visualize what your model is thinking, so in this case, the model is thinking it's more likely, for example, that you'll go from New York to the West Coast than to kind of, I guess, the middle of the country. So you might be able, so if it's a novel visualization, it's interesting in itself. If it's a visualization that's informative, you might be able to obtain interesting insights. So here, well, it's not really a groundbreaking insight that you're more likely to go to LA than to Kansas City from New York, right? People know that. But still, it's nice to confirm. So, okay. So here's the next idea that we introduced in the paper, and so this is not, I would be very happy if you do this kind of thing. At the same time, I don't necessarily expect that you would, because here, so this is an idea, one that might have worked out, might not have worked out, and there is like basically an amount of luck in terms of coming up with this kind of idea, right? And the idea is like that. So the way we'll compute the probability of going from location I to location J in time tau is we'll basically compute the product of this function r of the distance between I and j and the time interval tau and aj. Okay, so distance ij, that's the distance between I and j. Tau is the time interval, we just plug it in. R is some function that will actually figure out what the best function is. And aj is what we call the desirability of destination j. And again, we'll figure out the desirability of each destination j from the data. So you also need to divide by this denominator, but this is just to make sure that Pij tau is actually a probability in the sense that it kind of ranges from 0 to 1, and if you're starting at I, then all the probabilities of going from I to j, they all add up to 1, right? Because like you're gonna go from I somewhere, including maybe I itself, right? So this is what the denominator is for. So I'm not gonna go. You can read the paper, or you can kind of like stare at the slide in order to understand it. I'm not gonna go into details of how to actually obtain those desirabilities from the data, but you can obtain the desirabilities from the data. In other words, you obtain the best set of desirabilities that fit what you see in the data the best. And by seeing the data, I mean like by looking at all the people moving around everywhere. And in the same way, you can figure out, okay, like what's the best R that would take in the distance between I and j and the tau and produce the best probabilities. So we'll talk about learning with maximum likelihood, maybe kind of week 1 or week 2 actually of SML310, at which point you'll see more of it. But at this point, it's just about understanding, okay, we figured out that this kind of formula would work, but we don't know the AJs and we don't know the R, but we can figure them out from the data. So if you do figure them out from the data, you might start getting really interesting visualizations. So here, for example, I'm looking at what falls out of the data if you make the best model possible for making the best probabilities possible. Here are the most desired destination, and most desired has like a technical meaning. The AJ, alpha J here, sorry, is as high as possible, right? So we can compare it to just like the most popular destinations, which means like the destinations which the most people go to in our data set, and those are not necessarily the same, right? So a location, and in fact we see that a location like Sydney or Melbourne, they might be desirable, right? But they're so far away that they're not as popular as they might have been if they had not been so remote. And in fact, you see, so like stuff in Australia is desirable, but kind of Australian cities are not on the list of the most popular destinations. As you can see, there is a lot of overlap here between most popular, meaning lots of people in the dataset go there, and most desirable, meaning high alpha J, with the alpha J's obtained from the data in a way that obtains the best probabilities of transitioning from every location I to every location J. So there is some overlap, but there is some difference. And to me, and not just to me, like when I presented it, people liked it. This kind of thing makes for a good project. You get arguably some insights from the data. Now, I should caveat that, like, did we really get insights of what's most desirable? Well, kind of according to the formula. At the same time, if the most desirable destinations were completely different from the destinations that we knew to be the most popular, we would just say, well, the model's wrong. But if we're not saying, well, the model's wrong, well, kind of it's not really telling us much that's new. Now, you can apply it to data that you don't have preconceived notions about. So, for example, Shanghai. I don't know much of anything about the geography of Shanghai. What we do find is that the Shanghai airport, which is kind of like on the outskirts of the city, is desirable but not that popular. Which, again, kind of the same, we hypothesized that it's the same effect as with Sydney and Melbourne, where, yeah, you'd like to go to the airport, but it's kind of far away. Also, of course, there's other issues with airports. So next, and this is the kind of thing that you might come up with maybe if you already have the previous model. So if you already have this idea, and by the way, at this point we've got to say that if you take the log of both sides, you can kind of say that the log of the probability of going from I to j in time tau is like this, right? So it's like, and here we transform r to rho, so rho is just log r, and alpha is log a, right? And then you subtract log the denominator, but you can ignore that. So in some instances, so this becomes the log of Pij tau, and at this point you might say, okay, so our model is not anymore spatially invariant, and it's not directionally invariant. So we care about what destination we're going to. So are we going to, is this destination in the middle of the ocean, or is this destination like, New York City or London or something like that, where there's a lot of connections to that place, kind of by air, rail, whatever, right? But what this is not taking into account is kind of special affinities between the source and the destination, right? So one obvious example is probably most people, all things being equal, would travel inside their own country rather than go across the border, right? For one thing, you need a passport. It's like more complicated. There is customs So you would probably hypothesize that for like equal distances and equal attractiveness of destinations, you'd probably stay within the same country rather than cross a border. Right? Might not always be true, of course, but on average, probably true. So in order to capture this, what we do is we say, okay, so log pij tau is going to be what it used to be before, but now we're adding a new term. So this is ui transpose vj, or ui dot vj if you like linear algebra. So ui and vj are both what we call latent vectors. So those vectors attach to every location. So every I has a ui, it also has a vi. And now what we do is when we try to figure out the probability of going from I to j, we take into account the distance and the time interval, we take into account the desirability of destination j, and we also take into account this term, which depends on both ui and vj. And ui and vj, so those are like characteristics of the source and the destination. And we don't start with any particular values for ui, vj, we just find the ones that work best, that produce the best probabilities of going from I to j, right? And this term, if it's positive, it increases the probability. If it's negative, it decreases the probability. And it's supposed to represent kind of the affinity between location I and location j. So one example of affinity is, within the same country. Another example of affinity might be there is like a trade connection, right? So there might be kind of within the same state, whatever. So what we then go through is, again, we find the best probabilities by finding the best rows and the best alphas, the best u's, the best v's. And again, we might ask, okay, can we look at those affinities and find anything interesting? So I was presenting his work in Montreal last time, which is why this slide has transitions from Montreal. And you do see, so here kind of like, so this is just for the affinities. This is not for the probability of transition. This is more kind of for on top of the desirability of the destination and the probability just based on the time tau that it took to get there, and the distance between I and j. Is there like an extra connection? And what you see, so Montreal is of course in the in Quebec, which is the French-speaking province in Canada. And what you see is, in fact, there are positive affinities between Montreal and other locations in Quebec. Interestingly, also a location in New Brunswick, which is a bilingual province in Canada, so French and English are both official languages in New Brunswick, and in fact, there is positive affinity going from Montreal to the French-speaking part of New Brunswick, which is kind of cool. And as you see, there is actually kind of like less affinity than you expect between Montreal and I guess the Northeast, but more than you'd expect between Montreal and so both kind of Seattle and Vancouver, and I guess this would be LA. Okay, so we'll skip over that, and we'll go more to analyzing affinities. And this is again the kind of thing that if you have a model with something like affinities, something for you to think about, right? So here what I did is I plotted the average affinities for pairs of locations within borders and across borders. And what you see is that, yes, in fact, on average, the log affinity, so u dot v, is higher for pairs of locations within borders and across borders. So our model kind of knows that people, all things being equal, would prefer, well, not prefer, but would tend to stay within national borders. The next thing I was wondering about is, what about across languages? So there's obviously kind of a lot of the time cultural connections based on linguistics connections. So would people, all things being equal, tend to stay within the same linguistic area? And there the answer is kind of complicated. So for Spanish, it appears that they would. On the other hand, for English, there is not a clear pattern at all, right? So here we're disaggregating data by the distance traveled. And for English, well, like if you squint a little, you might be able to see some patterns, but basically no. And, one possible explanation is that a lot of kind of Spanish-speaking countries also border each other and have, strong cultural connections. Whereas with English, well, obviously not all English-speaking countries border each other, but also there is a lot of diversity in terms of where the countries are, like why is English the first language, and so on. So for Russian, again, it seems like people do tend to stay within Russian-speaking locations, and this is just across borders, right? So, kind of with Spanish, obviously, with English, obviously, lots of things are going on. With Spanish, a lot of what's going on is Latin America. With Russian, mostly we're talking about Russia and countries that border on Russia, sometimes having Russian as an official language as well. With French, you see a pattern where, well, you could argue no pattern, or you could argue, well, kind of there are connections, but not long range connections. In fact, there's like less affinity that you'd expect for distances of 5,000 kilometers. So I don't really have conclusions here. You just have kind of like observations. But again, so I think there were kind of neat observations and people liked them, and this got published. So this is one direction in which you can think, how can I kind of visualize the model that they fit to the data in a way that provides some kind of some kind of insight that I would not have otherwise. And again, a word of caution, this applies to this work as well. If I didn't see any patterns at all, well, I might say, oh, like the model is wrong. On the other hand, I see like, oh, there is a pattern with Spanish. I start thinking, oh, well, like maybe because of Latin America. And I see no pattern in English, and I say, oh, well, maybe because like all sorts of countries for all sorts of reasons have English as their official language, so stands to reason that there would not be kind of special connections. Even still, kind of data visualization, data exploration is a valid undertaking. And again, kind of as you're thinking about the projects, think about, okay, like could we obtain insights from data in this way?